Here I'm going to wrap up my lecture on the finite element simulation of the forging problem. And we were looking at the frictional case. So if I go to connections, contacts, and the contact between the tool and the workpiece is set to be frictionless with a friction coefficient of 0.1. And if I look at the deformation, this is undeformed. So I can turn on the deformation to true scale, and so we see that the workpiece moves by point. The top moves by point or 1 millimeter. So if you look at the displacement, that's at the top is 1 millimeter. This is very stiff. So so it moves by 1 millimeter. There is something funky going on here. I'm not sure how to fix that, and I'll see if I can have an Ansys engineer weigh in on that. I can also plot the total deformation for both the tool and the workpiece. So if I add that and I say retrieve this result, and if I have it to true scale, I see that the workpiece extends almost to the end over here. That may be part of the issue. So perhaps one could make the tool a little bit longer. So so if I look, I can go to the sigma yy, which is what I'm interested in, and if I look at if I do probe, I can probe the values over here. And let me actually go back to the undeformed view, and the minimum is around 740 megapascals. I've set the units to millimeters, and the actually this is here it says the minimum, but that's the most compressive stress. So in magnitude, this is the highest, and then it's 460 over here. And one can compare that to the analytical result. And so one can go back to the analytical solution and plug in the inputs for sigma naught, mu is 0.1, a, etc. And I got a range between, in terms of magnitude, between 462 and 762. Whereas here we get about 740 to 461. So this is very close, and that's actually the value that one gets in with the frictionless, and then this is the this is the upper value. So there's a slight mismatch, but not major. And one can actually plot that variation along that along the lower edge. What I'll do is, that's called a path plot. So I'll define a path along the lower edge and plot sigma yy along that edge. I'll go to model, and then I'll say construction geometry path, and it says, it gives you the option to define it using 2 points. The origin is over here, and then the end is going to be 50. So you see I have a line there, and then now if I highlight solution in the tree, and actually what I'll do is I'll just duplicate the previous entity I had. I'll say duplicate without results, and I can right click and rename. So I'll call that sigma yy along lower edge. And for scoping method, I change it to path, and the path we use the default name, so that's also called path. If I look over here, I can, I could have called it lower line or something. And so that's sigma yy, normal stress in the y direction, so I'll post-process that. So that plots sigma yy along there, and I can look at it as a graph, and this, you can either use the snipping tool. Actually, the best way probably is to use the snipping tool to snip that, and to, if you want to include that in your report, for instance. Or one could actually also go to tabular data, and I could do Control A, Control C, and copy this into Excel. So that's another way to plot it. You can plot it in Excel. All these values can be copied into Excel. And one thing we need to do is check mesh dependence. By the way, if we look at the variation, the max and the min magnitudes match with the theory. However, the variation is supposed to be exponential in between, whereas we are getting this kind of stepwise variation, and I'm not sure why that is. I don't have an explanation for that at this point. That is all there is to the simulation. So I will go into Workbench, and I'll say File, Save, and I can overwrite. I opened this from an archive, so I'll just overwrite the archive and save everything.